So for number 56, we've got a 5 gram bullet traveling horizontally with a speed of 1,000 meters per second. It hits an 18 kilogram door, embedding itself 10 centimeters from the side opposite the hinges. The 1 meter wide door is free to swing on its hinges. Before it hits the door, does the bullet have angular momentum relative to the door's axis of rotation? And the answer is, you sure bet it does. So we're using the other equation for angular momentum, mv, r perpendicular. Plugging in the numbers, velocity is 9. The distance is actually 90 centimeters away from this edge. Because the fact that it's hitting at that point 10 centimeters from the far edge, and it's a 1 meter long door. Solving it gives us angular momentum of the bullet relative to the hinge, 4.5 kilogram meters squared per second. Question BS, is mechanical energy conserved? Just with any kind of collision in this case, no, there's definitely going to be heat generated as the bullet hits. C, what's the angular speed does the door move immediately after the collision? So for C, what we have is this. The bullet is now embedded in the door, and the door is going to begin to rotate this way. The first thing we have to do, though, is figure out what the rotational inertia of the door is. It's that of a rod pivoting at one end plus the rotational inertia due to the bullet. Rod on one end, if you look at your table, is 1/3 ml squared. And the bullet's just a point mass that's that far away. Mass is 18, length is 1. Bullet's mass is 5 grams, and it's 0.9 meters away from the pivot point, giving us that. What do we know has to be true? Angular momentum must be conserved. Angular momentum beforehand was 4.5. That has to equal to I times omega. Plugging in the I from up above, for all practical purposes, we really could drop this term. It's so small, but I'll leave it in there for the moment. And if you solve this, we'll get that the omega of the door right after the bullet hits is 0.749. D, calculate the energy of the door bullet system and determine whether it's less than or equal to of the kinetic energy of the bullet before the collision. All right. So first of all, figure out the kinetic energy of the bullet beforehand, 1/2 mv squared. Plugging in the mass and the velocity, we get the initial energy of the bullet is a ridiculous 2,500 joules. What's the energy of the door afterwards? Well, it's rotational kinetic energy, 1/2 I omega squared. We know that I is about 6. I actually dropped off the small term this time. And omega from up above is this. Solving this one, we can very quickly calculate that the rotational kinetic energy afterwards, 1.68. Yes, that is significantly less than the energy of the bullet beforehand. Where'd all the rest of the energy go? Into heat. I hope this helped.